Today we're going to look at systems of linear inequalities applications. This video will be very similar to the linear inequalities applications video and notes, just now it's a system. So instead of just looking at one inequality, we're going to look at 2 or 3 inequalities. So example 1, to buy a quilt, Bradley is buying fabric in 2 colors, blue and red. He needs at least 9 yards of fabric in total. The blue fabric costs $8 per yard and the red fabric costs $12 per yard. The quilter can spend up to $120 on fabric. So what's going to be the trickiest for students is making sure that you're picking the right form and making sure that you're putting the right numbers together. So you have 2 constraints in this problem. You have a constraint on the amount of fabric that Bradley can get and how many yards he can purchase. And then you also have a constraint on the amount of money that he can spend. So one of your inequalities is going to have to do with the yards of fabric, and one of the inequalities is going to have to do with the amount of money that he's spending. So for part A, write an inequality to represent the length constraint. So what's my constraint on the length? He needs at least 9 yards of fabric. So he needs 9 yards or anything greater than 9 yards, okay? And of what? Of the fabric. So we have 2 types of fabric. We have the blue fabric, which is X. In addition to that, we have the red fabric, which is Y. And in total, both of those need to be greater than or equal to 9. Okay, so that would be the inequality to represent the length constraint. For the money constraint and the cost, I have 3 different values. I have the blue fabric is $8 per yard, the red fabric is $12 per yard, and the total that he can spend is up to $120. So if it's $8 per yard for the blue fabric, that's the rate of change. That's the cost every single yard for the blue fabric. So that would be written as 8x in addition to the red fabric, which is $12 per yard. They are both getting a variable because they are both rates. We're paying for the blue fabric, which is X, and the red fabric, which is Y. And then the quilter can spend up to $120. So that would represent a budget. That would mean that he can't go over $120. So my inequality for my second one would be less than or equal to 120. So now we're going to look at graphing it. Again, when you're graphing it, you guys can utilize Desmos. You can take the inequalities and change them into slope-intercept form. We saw from the word problems before that that tends to be a little bit more difficult just because the scale can be off and then that can change how we graph our slope. So it might just be easier to go straight into Desmos and see where the x-intercept and the y-intercepts are and just connect those 2 points. So the y-intercept for the first inequality, so I'm going to graph the x plus y is greater than 9 first. So the y-intercept is right here at 9, and the x-intercept is also at 9. Now, our scale goes by 2s, but that's totally fine. 9 would just be directly halfway between 8 and 10. Okay, and then this is a solid line. Then my second inequality was the 8x plus 12y is less than or equal to 120. So on that one, my y-intercept is at 10. And my x-intercept is at 15. okay? And then we can see that the shading is in between, which makes sense because we needed more than 9 yards. That was represented by that red line. That's my length constraint. And then I needed to spend less than 120, which is represented by the blue line. That's my cost constraint. So that means that all of the solutions for how much fabric he can purchase would be in between those two lines. Now, it's important to remember, we talked about this when we did inequalities the first time, is that we are restricted to the first quadrant here. So even though in Desmos, the graph is going to keep going, it's going to go past the X and Y intercept, we're talking about yards of fabric. So we cannot have negative yards of fabric. We cannot have negative money that we're spending. So this is going to remain all in the first quadrant. So our shading should remain in the first quadrant, and our line should be a segment. It should not continue on forever. So for part D, there's a lot of flexibility here on what answer you want to write down. What is one possible amount of blue fabric and red fabric that Bradley can purchase? You have choices of anywhere in the shaded region. Okay, so any point that falls into that area would be a solution. So we could say, let's say 6 yards of blue fabric, and we'll go right in the middle, 5 yards of red fabric. So 6 yards of blue fabric and 5 yards of red fabric. And both of these lines are solid lines, so you could also pick anywhere on the actual line, and that would be a solution as well for how much fabric he could purchase. Example 2, Mary is making muffins using blueberries and bananas. Blueberries cost $6 per pound and bananas cost $2 per pound. She wants to spend less than $72 on supplies, but also wants to purchase at least 10 pounds total of blueberries and bananas. Okay, so write a system of linear inequalities to represent the situation. So we have two constraints. One of our constraints, again, is money. She wants to spend less than $72 on supplies. So we should be setting up one of our inequalities based on that information. And then the second constraint is in the weight. She wants to purchase at least 10 pounds of blueberries and bananas. So that's going to be our second inequality. So for the first inequality with our cost constraint, what do we know about cost? We know that the blueberries are $6 each and the bananas are $2 each per pound. Okay, so X is the pounds of blueberries, which means we would write 6X plus it's $2 per pound of bananas, and she wants to spend less than $72. So this literally, the key word here is less than. So this inequality would just be less than 72. It doesn't say she wants to be equal to 72. She wants to spend less than that amount. Okay, but she also wants to purchase at least 10 pounds of blueberries and bananas. So for our second inequality in the system, it would be 10 pounds would be the total. And what is she purchasing? She's purchasing blueberries and bananas for a total of 10 pounds. And she wants at least 10 pounds. So that's another one of our key words that would be greater than or equal to. Okay, so then we can use Desmos. We can zoom in. This scale is really drawn out. And we also need to be careful that we're typing it into Desmos correctly. This actually should be a dashed line. But when you type this inequality in, that's what you would be able to see on your screen. So again, hard to see when it's zoomed out, but if you zoom in all the way, you can see that for that first inequality for that dashed line, the y-intercept is at 36. So I can graph a point at 36, and then the x-intercept is at 12. And again, this should be a dashed line. Okay, and then for the second inequality, the x-intercept and the y-intercept are both at 10. So look at your scale. It's going by 4s, so we have to think about where 10 would fall. 10 would be halfway between 8 and 12. So we can put a point here. And on this side, it hits exactly at 10. And that one would be a solid line. All right, and then the shading on this one is very similar to the last one, and it's in between the two lines because we want more than 10 pounds, but we want to spend less than $72. So we're meeting in the middle, and that would be my shaded region. So for example 2, is the point 418 a solution to the system of inequalities? And what does it mean in the context of the problem? So look back at your graph. You can plot the point using Desmos. If your graph looks like it's a little bit off, I would maybe utilize Desmos and really zoom into that coordinate. But this is a solution. The more difficult part of this question is, what does it mean? What are we talking about here? We're talking about blueberries, we're talking about bananas, is this money? What is it? So if you look at your graph, the x-axis represented the pounds of blueberries and the y-axis represented the pounds of bananas. So since 4 is x and 18 is y, that means 4 would be the pounds of blueberries and 18 would be the pounds of bananas. So this means because it is a solution, Mary can purchase 4 pounds of blueberries and 18 pounds of bananas. And you could even go further and say she's within her budget. You could plug it into the system of inequalities to prove that it's a solution and make sure that it holds true. That would be fine too. Checking the shaded region or plugging it in, either one works. And if you plug it in, then you could say exactly how much money she would spend to make sure that she is within her budget of $72. So if Mary purchases 6 pounds of blueberries, how many pounds of bananas can she get? So you have choices here. You can go on your graph to 6 pounds of blueberries, so on the x-axis, and just look to see what are my different options for how many pounds of bananas she can get, okay? I can also substitute 6 into both of my inequalities. So one of my inequalities was x plus y needs to be greater than or equal to 10, and the blueberries was x. So 6 plus y is greater than or equal to 10, so that would mean that y needs to be greater than or equal to 4. So if she gets 6 pounds of blueberries, we automatically know that she needs to get at least more than 4 pounds of bananas. However, that doesn't just keep going on to infinity. There's a restriction on the top end for our maximum number of bananas. So if I use my other inequality, which was 6x plus 2y is less than 72, I can plug in 6 for x into this inequality as well. And that will give me the maximum number of bananas that she can get. So we would subtract the 36. 2y is less than or equal to 36. Divide by 2, and y needs to be less than or equal to 18. So combining these two answers together, for my y value, she can get anywhere between 4 and 18 bananas, okay? And we can write that into a sentence. So she needs to get at least 4 bananas, but less than 18. And we need to be careful here because this actually would not be less than or equal to, because she wants to spend less than $72. So this would just be anything smaller than 18, but not equal to it, but anything bigger than 4 would work for the number of pounds of bananas that she could get.